Okay. Okay. So I've got the PhET simulation started here, and what we have is we've got the ground. We've got this little guy who's going to be pushing on a heavy file cabinet, and we got a free body diagram that shows the forces on the file cabinet. I don't know if you can read this, but the file cabinet's mass is 200 kilograms, and so multiply that by 9.8 to get the force and of gravity. Now notice that the gravity force in the free body diagram is canceling the normal force. They labeled it F sub n. And the cabinet is just sitting there. There's just those two forces. But now I'm going to ask the guy to start pushing on the cabinet. Now take a look at the two vectors here. I've got the blue vector pointing to the right, that's the applied force, and going to the left, that's the friction force. Now, which type of friction do we have here? Okay, if you said static friction, you're right. Now, take a look at what happens. Keep an eye on the red friction force. We're applying more and more and more and more. Something's going to happen to the red friction force at some point. Watch what happens. Right now the red friction force is sort of disappearing off to the left, but you can see it on the free body diagram. Pushing hard. Oh! What happened to the red friction force? I'm going to stop pushing. Okay, did you see that red vector was getting bigger, 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 and then as soon as the file cabinet started to move, what happened to that red vector, the friction force? Did you notice that it suddenly got smaller? That was the transition from static friction to kinetic friction. And one of the really interesting things about friction is that the kinetic friction force is always less than the maximum static friction. Let's see if we can do that again. I'm going to be pulling this time. So I'm now pushing, well, I said pulling, but I'm pushing to the left. Look at the red friction force vector. Pushing, pushing, pushing. This is still static, right? Static, 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 static. And oh, suddenly the red friction force vector is less. And yeah. So also notice that the friction force disappears entirely once the cabinet stops moving. Okay, so I think that that makes the point I was trying to make. I'm going to stop now and go back to the notes. Okay, so what I have now is a setup in my notes, which is very similar to the demo that you were just looking at. Now, okay, before I move on, I want to point out that everybody can get to the PhET simulations. So it's phet.colorado.edu, or just Google Physics Simulations, University of Colorado. And I think it'd be worth your while to play with this demo, or with this forces in one dimension simulation. You would learn a lot. Anyhow, let's run through an example with numbers attached to it. So I'm saying here, the trash can's weight is 200 newtons. How hard do you have to push it to move it? Okay, so this is a static friction problem because the question is essentially saying the trash can is not yet moving. The trash can is just there, not moving, and you're going to be pushing, pushing, pushing until you defeat the static friction. And so just before it, the instant before it moves, you've gotten to the answer, basically, how hard you have to push it. Okay, so you need to know some things. You need to know the static friction coefficient, and so you need to know this right here, the static friction coefficient. You need to know the normal force, right? Now, the normal force is going to be equal to the weight, right? And okay, so in order to get it to start moving, you have to defeat the static friction. In other words, your pushing force, I call it F sub P, has to be bigger than or equal to the static friction, maximum static friction, and that is mu s, the static friction coefficient, times the normal force. But here I put W because the weight is equal to the normal force. So anyhow, putting numbers in, you've got the static friction coefficient of 0.6 and the normal force of 200 newtons. Multiply and you get the answer, 120 newtons. Now, the next question is, if you want to keep it moving, how hard do you have to keep it moving? So if you just want to keep it going at a constant velocity, which is really what I'm asking here, your pushing force has to balance out the kinetic friction. Kinetic, because you're moving. So you want the pushing force to be at least be equal to the kinetic coefficient, which is, I'll switch to red here. Here's the kinetic friction coefficient, times the normal force, which was 200 newtons, and so you get the answer. 0.5 times 200 gives you 100 newtons. So this 100 newton would be just enough to keep it moving. Okay, so we're going to do a slightly different problem now. We're going to calculate the kinetic friction coefficient of an object, in this case a box on a tabletop, sliding to a stop. So the scenario is we have a box of mass m, and it has an initial velocity, which we'll call v sub 0, and the beginning of the experiment starts at time 0. And so the box starts out sliding and it's moving and then slowing down, and finally stopping. And we're going to be given the time that it took to come to a stop. We'll call that t-stop. We know that the final velocity is 0, and we're going to be given the distance that it took for the box to come to a stop. Notice that the mass is not going to be given, and you might think, oh my God, we can't do this problem if we don't know the mass. But it turns out that the mass is not necessary, and when you do the math, the mass will cancel itself out. It's a multi-step problem, which is kind of typical of friction problems, and so in the broad outline, we're going to start by figuring out the acceleration. We're going to then figure out the normal force. We're going to figure out the friction force, and then we're going to put the acceleration and these forces together and get the coefficient, the kinetic friction coefficient, which is what we are being asked to do, right? What is the friction coefficient? Okay, to get started, we need to figure out this acceleration. Now, one simplifying thing about kinetic friction is that the friction is constant. It doesn't matter how fast you're moving, it's the same amount of friction. If it's the same amount of friction, the same amount of net force, then it's going to be the same acceleration. The acceleration is constant. If the acceleration is constant, then we can use the big five equations, right? That's what they're for. They're for situations where the acceleration is constant. So looking at the formula sheet, big five, equation number 5 is this one. This is the one that is going to be appropriate, right, given all the things that we know and don't know. So v squared, the final velocity squared, equals the initial velocity squared plus 2 times the acceleration times the distance it took. Okay, we're after the acceleration, so we want to isolate a. So we're going to subtract v0 from both sides. We're going to divide by 2, and we get ax minus x naught equals 1/2 v squared minus v0 squared. Now, the x0, the initial position, is 0, so it kind of goes away anyhow. And the final velocity is 0, so it's going to go away. And so now we can divide both sides by x to get a formula that'll work pretty well. And we have that a equals 1/2 times negative v0 squared divided by x. And at this point we can plug in the numbers. Okay, we have negative 1/2. The final velocity was, the initial velocity was 20 meters per second, so that gets plugged in. The distance that we were given to stop was 25 meters. Plug it all in, and you get negative 8 meters per second squared. The negative sign makes sense because it's a de-acceleration. Okay, so now we need the normal force. Now, the normal force, which is what's holding it up, is equal to the weight, right? So the normal force and weight cancel. So the normal force equals mass times gravity, but we don't know the mass. So at this point, you have options. You could work your way through this problem in an algebra sort of way, which is actually better, to be honest. But what I decided to do here is show you a little trick. In these situations, you could just make up a mass. And a nice mass to just make up is 1, because 1 is an easy number to deal with. So let's just suppose the mass is 1 kilogram. Then the normal force is mg, 1 kilogram, times 9.8 newtons per kilogram equals 9.8 newtons. Okay, we now know the normal force. So, okay, now we want to know the friction force. Okay, so the friction force was the mass times the acceleration. Now we figured out the acceleration, right? The acceleration was the minus 9.8 meters per second squared. Looks like we don't really need the negative sign anymore. We just care about the magnitude of the friction force. So we are only going to need the magnitude of the acceleration. Mass times acceleration. Okay, well, we're going to use the same. You got to be consistent, right? If you chose 1 kilogram here, you got to choose 1 kilogram here as well. Multiply it, and you get 8 newtons. Okay, now remember, we want to figure out mu sub k. So here's the friction formula. The friction equals the friction coefficient times the normal force. Solve for the friction coefficient by dividing both sides by the normal force. And so we have the 8 newtons divided by 9.8 newtons, and you get 0.816. So yeah, there you go. We've got an answer. By the way, you may say, wow, this is weird. There are no units. And so, yeah, it turns out that the friction coefficient is a kind of number known as a dimensionless number. Okay, now I'm not completely happy with my explanation here for how the 1 kilogram went away, the mass went away. So I'm going to show you how this works the algebra way. So what we have is that mu k, which is the friction force over the normal force. Now, this friction force is equal to mass times acceleration, right? That's this over here. And the normal force, which is equal to the weight, is the mass times gravity. Notice how the masses cancel. So the friction coefficient is A over G. And so let's see, we have that the acceleration was 8 meters per second squared, right? That came from here. And gravity is 9.8 meters per second squared. Notice the meters per second squared and meters per second squared cancel, and you get the same answer, 0.816. Okay, so we're going to do another one of these friction problems. This one is almost guaranteed to come up in a test or quiz or final exam. The question is, I've got an object which is sliding down an inclined plane, and the slope is set by this angle theta. What is the box's downhill acceleration going to be? And so we have that the box has mass m. Now I'm going to tell you right now, the mass is not going to matter. It's going to cancel out like before. The friction coefficient, that will matter. That's going to be important. And the angle will matter. After all, we know that the more steep the hill is, the more the acceleration is going to be. We just kind of know that. So the first step in figuring this out is to find the downhill component. In a rotated coordinate system here, you see I've rotated the coordinate system so that x points like this and y points like this. We want to know what this part right here is. You see, what makes the box go downhill is the weight. But in this rotated coordinate system, the weight breaks down into two parts. It decomposes, I should say, into two parts, into an x component and a y component. And it's the x component that makes it accelerate down the hill. Okay, now, from a previous discussion, you could go through the SOHCAHTOA and all of that, but you know that the parallel component is either going to be the weight times the sine of theta or the weight times the cosine of theta. So thinking in terms of what happens when the angle gets more and more until finally at 90 degrees, you know, it's like a cliff, right? It's sliding down a cliff. The acceleration is more and more. So that means that the x component of the force must be more and more. So at 90 degrees, which function is a maximum? Is it the cosine or is it the sine? And well, it's the sine. So I know that the x component is going to be the sine of theta times the weight. The x component of the weight will be this. And through a similar kind of logic, we're going to find out that the y component, this is the y component of the weight, is going to be mg cosine of theta. Now that's important because the normal force, which cancels out the y component of the weight, that's the squeezing force between the two surfaces, right? Between the box and the hill surface. And so the y component of the force is used in figuring out the friction. So the kinetic friction is going to be the y component of the force, mg cosine theta, times the kinetic friction coefficient. Okay, so we've got these two pieces here that are really important. We've got the x component and we've got the friction force. So now that we've got those two things, the downhill force and the friction force, we can figure out the acceleration. So, okay, the acceleration is the net force over the mass. And it's the downhill force. The net force is the downhill force minus the friction force. And we're going to be dividing by the mass. So here is the downhill force. Here is the friction force. And then here's the mass. Notice that the masses cancel out. So you're left with g sine theta and minus mu sub k, the kinetic friction coefficient, times the cosine of theta. And so, yeah, beautiful. Now you have a formula that gives you the answer to this sort of question. So you could plug in some numbers, let's say the friction coefficient was 0.3, the angle was 25, what's the acceleration going to be? So here you're plugging in the numbers and you get the answer, 1.48 meters per second squared. You didn't need the mass.